Hi folks, Chris McClure here. We now turn to section 4.6 where we will be looking at some counting techniques to allow us to better able to calculate the probability of some events. As we know, when we do the theoretical calculation of the probability of an event, some event A, what we need to do is calculate the number of ways that event A could happen divided by the total number of equally likely outcomes in the sample space. In other words, we're dividing by the total number of ways that we can get an outcome. And in counting the number of ways that our event could happen or total number of outcomes might require us to use an advanced counting technique. We'll look at some of those techniques today. We're going to be using the fundamental counting rule that says that if you have a sequence of two events, and your first event could happen in m number of ways, and your second event could happen in n number of ways, then the number of ways that those two events could happen in total, it will be just the product of those two numbers. So for example, suppose that you've got 5 ways of ordering a sandwich at a deli, and maybe there's 4 soups. Then that means that there are 4 times 5, which is 20 ways of having a lunch. Okay? Now, suppose that we have 4 books, and we have a bookshelf, right? We have space for 1, 2, 3, 4 books. Now, here we've got the 4 books in a pile right here, and we're going to arrange these 4 books on the bookshelf. Well, there are 4 books to choose from for the first book on our shelf. That's going to leave us with 3 books left in our pile. So that means there's 3 books to choose from for our second slot on the bookshelf. Then that leaves us with 2 books for the third choice and 1 book for the last choice. And there's going to be a total of 4 times 3 times 2 times 1 possible ways of arranging those 4 books on the bookshelf. And 4 times 3 times 2 times 1 is equal to 24. We're just using that multiplication principle. But this actually happens to be a very special product when you multiply an integer like 4 times all the whole numbers that are less than it. What we have done is calculated a factorial. 4 times 3 times 2 times 1 is 4 factorial. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is 10 factorial, which is going to be some number. It's 10 times 9 factorial. But 9 factorial is 9 times 8 factorial, and so forth. By the way, 0 factorial is equal to 1 by definition, even though 0 doesn't have any positive whole numbers below it, but by definition we'll call it 1. It doesn't make sense to have a negative number with a factorial, and we don't know what that is. We also, at least for the purposes of this discussion, we don't take factorials of fractions either. Only of positive integers do we take factorials of. Now, the factorial rule tells us how to do a permutation. A permutation is nothing more than an arrangement of so many items. And the number of different permutations, aka arrangements of n different items, in other words, the number of ways that the n different items can be arranged when all of them are selected, that's going to be the number of permutations. And it turns out that is going to be, n factorial. because there are n ways of choosing the first item, and n minus 1 ways of choosing the second item, and n minus 2 ways to choose the third item, and so forth, all the way down to 2 ways of choosing the second to last item, and then finally 1 way of choosing that very last item. So that's n factorial. The permutation rule says that, if you have n different items available and you are going to arrange all of them, then there's n factorial ways of doing that. But suppose that you select r of them, where r is less than n. So for example, if you have 10 potted plants, but you only have room on your shelf for 6 of them, so you will select and therefore arrange 6 out of the 10, for example, without replacement, which means that when we select an item, we don't put it back, we put it on the shelf. And order matters. If you have book A, book B, book C on the shelf, that's a different arrangement than book C, book B, book A. Order matters. When you have the same items but in a different ordering, then that's a different permutation. And it turns out that the number of permutations of R items taken from n items available is given by this. How come? Well, let's take our 10 house plants, and we're going to select 6 of them. There were 10 ways of choosing that first house plant, followed by 9 ways of choosing that second house plant, followed by 8, followed by 7, followed by 6, followed by 5. So there, whatever 10 times 9 times 8 times 7 times 6 times 5, whatever that works out to be, that's the total number of ways of arranging those 6 house plants from the 10 available. And what we mean by arranging is we're selecting them randomly. Now, we could go in our calculator, input 10 times 9 times 8 times 7 times 6 times 5. Or we could do this little trick here. We could multiply by 4 times 3 times 2 times 1. And also divide by 4 times 3 times 2 times 1. So when we do that, you notice that we've just multiplied by 1, which doesn't change anything. But, well, it doesn't change the value, but how this appears now in the numerator of this fraction here is 10 factorial. And divided by 4 factorial. But 4 factorial, well, 4 is equal to 10 minus 6. So you have 10 factorial divided by 10 minus 6. And in general, if you have n number of items available and you're going to arrange r of them, then n factorial divided by n minus r factorial will be what counts the number of ways of doing that permutation. Okay? And remember, order matters for permutations. Now, we'll talk about the so-called Mississippi rule that says that, if you have 2 or more items in the set that you're choosing from that are exactly the same as each other, then not all rearrangements will be distinguishable for each other. And the reason that we call it the Mississippi rule is that if you look at the word Mississippi, notice that there are 4 I's, 4 S's, 2 P's. If you were to switch these two P's, or switch these two I's, or rearrange all four S's. Maybe take this S to be this S, and this S to be that S, and so forth. If you were to swap out any two letters that are the same, you would have an identical, non-distinguishable rearrangement / permutation. So if you only wanted to count the number of distinguishable permutations, like for example, if we were to swap this I with the M, we would have Mississippi. That would be different than Mississippi. If we want to count the number of distinguishable permutations, then this is what does it for us. You take the total number of items available, which for the word Mississippi, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 letters available to it. And then in the denominator, you're dividing by the number for each item that is the same. So for example, we have 4 S's. So we'll divide by 4. Because it doesn't really matter, if you were to rearrange any or all 4 of them. And likewise, there are 4 I's, so we will also divide by 4 factorial, because there are 4 factorial ways of rearranging them, which don't matter. And there's 2 P's, and we have 2 factorial in the denominator there. We have a 1 M. We could divide by 1 if we want, but that won't change anything. Okay? And 11 factorial over 4 factorial, 4 factorial, 2 factorial. Now you could multiply that out, and that's fine, using your calculator, because you know that 11 times, or 11 factorial is 11 times 10 times 9 times 8, times 7 times 6 times 5 times 4 times 3 times 2 times 1. Divided by 4 factorial, which is 4 times 3 times 2 times 1. And 4 factorial is 4 times 3 times 2 times 1. And then times 2 factorial, which is 2. But let me show you an easier way. I'm going to actually fire up my calculator here. I wasn't going to do it, but I've changed my mind. I'll show you how to do it on my graphing calculator. So if you wanted to calculate a binomial, a factorial, suppose that you wanted to do 11 factorial. So you just input the number 11, go in your math menu, probability, option 4, which is the factorial symbol, exclamation mark, and hit enter, and you end up with, what do we have here? We got 39,916,800. So that's the number of ways that you can rearrange 11 items. Now, if you wanted to evaluate this quantity here, the number of distinguishable permutations for the letters of the word Mississippi, we can do that too. In parentheses, we could do 11 factorial, and then close parentheses, divided by open parentheses 4 factorial times 4 factorial times 2 factorial, but 2 factorial is 2, so we'll just leave that as 2. And by the way, it's okay for you to leave these guys next to each other, because the calculator knows that that means to multiply. And we are left with 34,650. So there's 34,650 distinguishable permutations of the letters Mississippi. Okay? Now, if when you rearrange the items in your selection, and if it doesn't matter that you rearrange them, then that rearrangement's not going to matter. If you, for example, have selected 3 tiles from your Scrabble bag and you get ABC, well, as far as I'm concerned, in the game of Scrabble, ABC is the same thing as CBA. Also, in the game of poker, if you are dealt, a 5-card hand, it doesn't really matter what order you're dealt those cards. So, because as far as I'm concerned, an ace of hearts, 2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts is exactly the same thing as a 5 of hearts, 3 of hearts, 4 of hearts, ace of hearts, and 2 of hearts. So when the order in which your items appear doesn't matter, then it's going to be the combination which counts the total number of ways of selecting those R number of items from the n different items available without replacement. And here's how we calculate the combination. You'll notice that it's exactly like the permutation, where you have an n factorial over an n minus r factorial. But you're also dividing by an r factorial. So, for example, for a poker hand, how many ways can you select 5 cards from a 52-card deck? Well, there are 52 cards available. But you're selecting 5 of them, and the order doesn't matter. So in the denominator, you'll have a 5 factorial. That would be your r factorial. And then 52 minus 5 is 47. So you have a 47 factorial in the denominator as well. By the way, the notation that you see here is combination, right? Big C with a 52 to the lower left and a 5 in the lower right. And that will count the number of ways of choosing 5 items from 52. And again, that's where order does not matter. Likewise, if you have 20 people to choose from, but you need to select 5 to serve on a committee, well, there's going to be 20 choose 5, meaning the combination of 20 items taken 5 at a time, which is going to be 20 factorial over 5 factorial, 15 factorial. I'm going to show you something on your calculator. Most of your modern calculators have the capability of computing permutations and combinations. I'm going to show you permutations and combinations by talking about the poker hand. Now, if it turns out that order does matter for a poker hand, for being dealt 5 cards, and you want to do combination, sorry, not the combination, but the permutation, you want to do permutation of 52 cards taken 5 at a time. How many ways can you be dealt 5 cards where order matters? To do that permutation, what you do is you will input 52, go in the math menu, go over to the probability submenu, go down to NPR, and then select 5. And hit enter. So there works out to be 311,875,200 ways of being dealt 5 cards where order matters. Now, if order doesn't matter, you want to count the number of ways of being dealt 5 cards, then we'll do a combination. We'll do 52. Go back in your math menu, probability. Option 3 is the combination, NCR. And then hit 5, enter, and that is going to be 2,598,976. Excuse me, 960. 960. Okay? Just reiterating here that for the permutation, order matters. But if order doesn't matter, then you are going to be using combination. So here's some more examples here. Now, in computer science, a byte, B-Y-T-E, is a sequence of 8 numbers. all other either 0 or 1. So for example, a 1 0 1 1 1 0 0 1 would be 1 byte. And the total number of possible bytes is equal to 2 raised to the 8th power. Why? Because there's 2 choices for each position. You could either put a 0 or a 1 in each position. There's 2 choices for the first position, and 2 choices for the second position, and 2 for the third, 2 for the fourth, 2 for the fifth, 2 for the sixth, 2 for the seventh, and 2 for the 8th position. So you get 2 to the 8th power. And 2 to the 8th power is 256. So there's 256 possible bytes. Here's another example. Suppose that, in history class, the instructor gives a pop quiz. And in the pop quiz, you are asked to arrange the following presidents in chronological order. And in which order did these individuals serve as President of the United States? So you got these 5 names: Hayes, Taft, Polk, Taylor, Grant, and Pierce. I might have some challenge in trying to do that myself, unless I had studied this. So suppose that you walk in and you hadn't studied. Maybe you were sick the day before and you were completely out of it and you didn't get yesterday's lecture. So you come in today, you're given this pop quiz at the beginning of class. So you have to totally guess at it. You have 1, 2, 3, 4, 5, 6. So there's 6 ways of randomly selecting one individual, followed by 5, followed by 4, 3, 2, and 1. In other words, there are 6 factorial ways of ordering the service of these 6 people as presidents of the United States. But there's only one correct ordering. So you have a 1 in 720 chance of actually getting the ordering correct. If you were to take 1 divided by 720, you would get 0.00139. So there's a very small probability of getting this pop quiz correct. Now, hopefully, your history professor would have a little bit of grace in allowing you to make this quiz up by offering you an alternative after you've had a chance to study. Because after all, if you were sick, you were sick, right? Here's another example. Suppose that we're going to play the lottery. In the Pennsylvania Match 6 Lotto, we are going to select 6 numbers from 1 to 49. So there's 49 numbers available for each choice. You cannot repeat any numbers. It would be like having 49 balls with the number 1 through 49 printed on them in a bag. And you reach into the bag and you select one, and then you reach into the bag and select another one. You keep doing that so you have 6 numbers. And then the order doesn't matter in which you select these numbers. So how many ways can you select 6 numbers from 49? And the answer is going to be, 49 choose 6, like you see here. Here's the calculation. And you saw how to do it on the calculator as well. There it works out to be 13,983,816 ways of choosing 6 numbers from 49. But there's only one way of getting all 6 of your numbers to match the 6 numbers that get drawn. So this is the very small probability of winning the lottery. You have a better chance of being struck by lightning or being bitten by a white shark or getting a hole-in-one on the first time that you play golf blindfolded, probably. So I wanted to also do another problem with you, is that if you wanted to calculate the probability, actually we'll go back to this slide right here. If you want to calculate the probability of being dealt a full house, for example, and you could do this for practically any hand in poker. I'll just do it for full house for now. Suppose that you are dealt 5 cards from a deck of 52 playing cards. What's the probability that you are dealt a full house, which means that you have a 3 of a kind, which is a triple, and the other 2 cards are a double. So you have a triple or a 3 of a kind, and you have a pair. Hold on, let me fix that. Double. So you have a triple and a double. So let's see if we can calculate the probability of being dealt a full house when you're dealt 5 cards. Now we need to count the number of ways of getting a full house. So first of all, we need to choose a value for that 3 of a kind. There are 13 different values. So we have 13 ways of choosing the value. Once you choose the value, then there are 4 cards of the same value. Of those 4 cards, there's 4 choose 3 ways. By the way, this is a combination of 4 taken 3 at a time, of getting 3 cards out of 4. In other words, if I have 4 cards of the same value, there's 4 choose 3 ways of choosing those 3 cards. And then let's move on to our double. There's going to be 12 values that are not equal to the value chosen for the 3 of a kind. And of those 12 values, there's 4 choose 2 ways of choosing the double. Remember, there are 4 cards of the same value. So 4 choose 2 will count the number of ways of selecting 2 cards from the 4. And then there's 52 choose 5 ways of selecting 5 cards from 52. We already did that calculation. By the way, when I say N choose R like that, that means combination of N items taken R at a time. That's just a more compact notation. So let's go and calculate on our calculator how to, or what's the probability of being dealt a full house. So we're going to do this. There are, in parentheses, 13 ways of choosing that first value, that value for the triple, times. And now 4 choose 3 is 4, but we'll go ahead and do 4 choose 3. So there's 3. And then times, and make sure you use parentheses, by the way, when you input your combination like that. Then times 12 times, open parentheses, we'll have 4 choose 2. Close parentheses, maybe, divide by, open parentheses, 52 choose 5. Close parentheses. Enter. And there is the probability of being dealt a full house. It's approximately 0.00144. Okay, so if you were to play or be dealt a 5-card poker hand, say 1,000 times, you would expect to be dealt 1 or 2 full houses. That's one way of interpreting that probability. Because the probability is greater than 1 1,000th, but less than 2 1,000th. Alright, so that's it for today. That is it for Chapter 4. We're not going to do the other 2 sections because it involves computers, which we're not equipped to do for a face-to-face class. So as of now, We've covered all the material that we are going to for the exam. The first exam, which is a midterm exam, will cover chapters 1 through 4. I'm going to send out a practice exam momentarily so you can see what to expect regarding the actual midterm exam next week. If you have not yet told me where you are going to take your midterm exam, you need to email me that information as soon as possible so I can start compiling that in a spreadsheet. And so I know exactly where to email your test out to. Okay? With that, have a good weekend. I'm not going to post anything tomorrow, which is Friday the 13th, because I'm going to be traveling and out of town. So the next time you'll hear anything from me will be on Monday. So have a good day, and I'll see you later.